All right, so let me talk a little bit about partial derivatives. I won't spend too much time. You know how to calculate, just to show you some of the properties. And typically in a physics class it's not done, but again, I'd like to be thorough. I don't want to really distinguish math from physics, particularly in the theory class. So if we are relying on a mathematical result that I'm able to present, I would like to present to you. So let's look at this function. And I think we looked at this function. Or something similar. Let's look at x squared y, just so that, so it's function of x and y, it's x squared y. Okay. Let's take the partial derivative with respect to x. What do we get? Well, I know you know, that I know, that you know. So there it is. I'm not going to waste time. And then I'm going to do this is x squared. And then what I'm going to do is I'm going to take the mixed partials. This notation means first you take the derivative with respect to x, and then you take the partial with respect to y. So I take this function, and then take partial with respect to x, and I get 2x. Now I take this function and take partial with respect to x. So I do dx, well, the notation. And I get 2x. And you can clearly see that the order of partial derivatives does not matter. This is by and large true. By and large is not a good word, right? So let me show you a case where it's not true so that we can know what goes wrong when. So let's try a new, so let me call this example 1. And then the counterexample, and what have we learned, and what can we rely on in the future? So let me, again, f of x, y, I'm going to do just square root of x plus y. So df dx, 1 over 2 times square root of x, df dy equals 1. Let's take the mixed partials. D squared f yeah, that's not good. Let me make this y squared to make my point. So then this becomes 2y. No, let me make it y squared x. Yeah?
Magician of the problem.
Well, I have to think of it like a lesson learned. It's by and large true. So I have to work hard for it to be not true. Okay, let me take now this. Well, that's tricky. Oh my goodness, it is by and large true, isn't it? Quando, 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 quando. Ay, ay, ay. Let's see how it pans out. I think this is going to be true, but I'll think of a clever example. So then this becomes 2 times x plus 2y. Ah, don't tell me. That's by and large true. I'm going to work an example where it's not true. I don't want to waste your time, but my next lecture, I'll think of a counterexample. It's right there, but I can't think of it offhand. Let me tell you, but since I don't want to waste time, I'll just present the counterexample next time. But let me tell you when you know it is true. Because by and large, we will assume this. Well, by and large, it is true. Apparently, no matter how hard I try. So, here's the theorem. It's a theorem in math. Okay? If this exists, this exists, and this exists, and they are continuous. What does that mean? Continuous means if you graph it, it'll be, there's no holes. You don't have to take your hand out to draw the diagram. But for example, if I have the graph of a function, this function is continuous. Well, this is not. If value over here is that. So I have to take my hand off to draw the graph, right? And they're continuous, then the other one exists. And d squared f dx dy equals d squared f dy dx. What I was trying to do is to violate the continuity. How did I violate the continuity? Is by putting 1 over square root of x. This is continuous except at x equals 0. So I thought that would give us what we need, but it didn't. It didn't. The theorem doesn't say this has to be true. But if this is true, then that is true. In physics, typically we expect things to be continuous, except where physics is interesting. In this year, this semester, and next semester, we will have electric fields and magnetic fields that are not continuous. And the place of discontinuity is the most interesting area. That is where charged surfaces or current surfaces will lie. So it's a telltale sign of something interesting going on when you see a discontinuity. Okay? So in that case, you cannot just take these mixed derivatives. But here you are in space, charges fluttering about here, everything is continuous. Okay? But if you have a capacitor sheet, then the electric field will not be continuous. You know this from freshman physics, but you didn't see it in that flavor, that's all. Okay? So these are properties of partial derivatives. What must I do when I begin my lecture next time? To come up with a counterexample.
Bet against the house.
Exactly. Well, the problem is the house wins, right? Because when we think of functions, we always think of what? Continuous functions. But there are more discontinuous functions than continuous functions. Okay. And then going back to where we ended, suppose you have some function t, which is a function, I'll write this down as function of x, y, and z. And then I'm going to see how t changes along a curve. And a curve is described by some parameter s. Yesterday I made s go from, by yesterday I mean n minus 1. I made s start from s equals 0 to s equals 1. It really doesn't matter, some initial value to some final value. Okay? And then the rate of change of t as a function of s. Now, it's tricky because t is really a function of x, y, and z. T is defined in all space. But we're only looking at how t changes along this curve. And we surmised that this is written as dx plus dt dy ds plus dt dz dz ds. And I gave you an example of a curve. I'm going to revisit that example. And we'll also look at how t changes and try to understand its properties. So let me do a simple curve example. So consider the curve. We talked about it. I'll draw curves generally two-dimensional. They're easier to draw. I'll call this s x hat plus s squared y hat. I'm just going to look at the curve from S and belonging to the set. Well, that's just notation. That means S takes on every value between 0 and 1. You can extend the curve even beyond, but this is the initial value, that's the final value. And I think we discussed this. Okay. This is so look at this. This is my x value. This is my y value. So if y equals s squared, that's really y equals x squared. And that's a parabola. And I'm stopping here only because we just choose to. So the parabola starts here, and parabola ends here. And I can look at how t changes over this nice parabola. What's the tangent vector along the curve? Remember, just from calculus or physics, tangent vector is nothing more than the derivative, right? But this is a vector valued derivative. So this tangent vector, at any point, it's a straight line, it's an arrow. But this arrow depends on, obviously the arrow is changing direction. And this is nothing more than, okay, well, that is nothing more than 1 x hat plus 2s y hat. Fine. But now, let me consider another example. What do you think the graph of this function is going to be? I'm sorry? It is the exact same parabola. Because look, y equals s to the fourth, which is s squared squared, which is so the point is, if I have a physical curve of interest, I don't have a good choice of parameter. Normally, if I'm studying math. So I'd like to have a parameter independent notation. In physics we do. A good parameter is time. Maybe a particle is starting from one point and going through another point. What is the change in potential energy? Well, you would integrate the potential energy along the path. In physics we do. But this chapter is just vector calculus, learning all the tricks of the trade. The only difference is dx ds now is 2s x hat plus 4s cubed y hat. If you compute the change in change in t, you will get the same answer if you use both of the curves. So this actual dependence does not matter. Now you might say, well, how will I get the same answer? Well, this expression is important. So I'm not going to erase that. Well, the change, so let's say this is some initial point and this is some final point. Delta t, which is final value of t minus initial value of t, is really nothing more than dt over ds times ds from si to s. Right? Because from calculus, you just know that this is nothing more than dt. Because when you do dt, well, it's going to be, what's the integral of dx? It's the simplest integral you can do. Delta x, xf minus xi. Integral of dt, tf minus ti. Well, that's what I started with. So what is important, so this is some ti, tf. And when we do examples, this will be a little more concrete. But the point is, what we need often is this quantity. So this same equation will be written as dt equals, and all I'm going to do is take the ds away. It is to be understood that if you're evaluating along a curve, you'll have to divide, take the derivative with respect to the parameter. And so what is it? It's dt dx plus dt dy plus dt. We'll get to do examples. Yeah? This guy is called a differential. And they're made up. So this is a curious object. You don't know what this is, but whatever this is, it's equal to that. Fine. Well, that's just blaming someone else. You know what these guys are. You know how to take derivatives. You don't know what these guys are. It's back to the same problem. But remember, this is to be understood within the context of taking somewhere along the way, taking a derivative along the curve, and then integrating as needed. Okay, we'll give me a few more minutes and I'll do some problems. Any questions so far? No? All right. So, note, Martin wanted to very badly do the upside down triangle. So let's do it. I can write this as Because when I take the dot product, I do this guy times that guy plus this guy times that guy. And similarly for Z. Just using our notation. The gradient of T denoted by, so I'm going to take a scalar, a function, and make it a vector. So I'm going to have, your book just puts it in bold. Again, I don't come in bold, so. Is given by gradient n of t, or any function, it doesn't matter. Well, precisely this guy. So gradient takes a function and creates a vector. Well, vector field, vector in every point in space. You know, a good example for a vector field is like an electric field and magnetic field and so on and so forth. Okay, when am I doing examples? Okay, bear with me for a couple more problems and then let's do examples. This guy is denoted, it's a small change in displacement. So displacement, length in mind, this is denoted as dl. So literally what do I mean? dl is dx x hat plus dy y hat plus dz z hat. But you know what? Let me do an example, just so that you know you're comfortable in doing problems. Every time you see theory, you're going, well, that's great. How will an exam problem look like? Well, this is what an exam problem might look like. At the moment, example. X times y squared times z cubed. I'm just making all the exponents different. It's a so this is the kind of problem you want to beg for because it's a no-brainer. What would you do? Take the derivative with respect to x. What do you get? Y squared z cubed x hat. Take the derivative with respect to y. 2xy z cubed, correct? Derivative with respect to z, 3xy squared z squared. Simple as that, that's the derivative. So now I have taken a simple function and made it a vector. Vector at every point. The value of this vector depends on the point. Changes. If I were to plot it out, it'll look like arrow. I'm not saying what I don't know what the graph of this would look like, but when I say a vector field, as opposed to a vector, it'll look like it can change directions. Yeah. Suppose find gradient of f at the point, and I won't make it complicated. Let's say 1 minus 1, 2, just for. So then gradient of f at the point 1 minus 1, 2, well, you tell me what it is. This is 1, and this is 2. So it's 2 cubed. And then I have minus 60 y hat. Is that correct? If I gave you another point, it might look different. First of all, is that correct? What did I do? I put 1 for x, minus 1 for y. And yeah, let me do a simple point. Just to show you, well, did that because it says at the point 0, 1, 1, that's equal to x hat. Because the fact that there's x in these two kills that one. So you can see at the point 0, 1, 1, that's the vector. It's 1 times x hat. But at a different point, it's another vector. So these vectors are changing length and direction, magnitude and direction. So when you graph it, it'll fill all of space, but it'll just, it'll be like something, it could be, it doesn't have to. It could even go out, it could curve. These are all words I'm dropping. We're going to compute the curve. We'll have to see what that means. It can diverge like a sprinkler spraying water, or it can converge like a sinkhole where water falls in, or it can curl about like vortices. We'll see all of that. We'll have divergence theorem. We'll talk about the curve, and so on and so forth. So let's back to the gradient. So we know how to calculate gradient. What does gradient mean? So dt, I can write it as gradient of t dot, what did I call it? dl. And I know how to take dot products. We learned that last week or last week sometime, yeah. It is the magnitude of this guy times the magnitude of that guy times the cosine of the angle between them. Correct? So to get the meaning, let me write the following sentence. I wrote it down. dt is a maximum, max, when dl is parallel, no, along the direction, of gradient of t. What does that mean? First of all, let's see if this is true, and then I'll write the meaning. So what we're going to do is suppose you are starting off here. This is my initial point. Yeah? And I evaluate the value of t here. Now what I can do is I can evaluate t along any curve. I can go this way, I can go that way, I can go this way, I can go that way. Yeah? Let's say, well, gradient of t is a vector. So at this point, it might point in this direction. This is gradient of t. So if I take my curve and go along the direction of gradient of t, that means what is the angle between them? 0. And cosine of 0 is 1. That's when this is a maximum. Because these two are fixed, I'm going to go a certain length, maybe like 1 meter. These two are fixed, but I only get to play with the direction. But if I go in the direction of gradient of t, I get the maximum change in t. So what does that mean? Gradient points in the direction of the maximum change of the function. So if you are climbing a hill, and at any point you compute the gradient, and you climb along the gradient, it's the steepest climb you'll have. Yeah? And if you climb against the gradient, it'll be the, well, downward maximum steep. Yeah? So let me write that down so that you have it in your notes as well. The gradient of a function points along. I'll do plenty of examples. Huh? I just tend to do a little bit of language and theory to develop it. But you will have a problem day in class so that all of this will be fleshed out. The gradient of a function points along the maximum change of the function. And so gradient of t is thought of as something acting on t. The del operator acting on t, where it's pronounced del. Del, by definition, is equal to correct? So when del acts on t, you would act it on t, which means for this, here you would put t, here you would put t, here you would put t. That's just language. Any questions? So I'm going to bring it a little closer to physics. I'm going to talk about the position vector and the displacement vector, and then we'll do some problems. Okay, so I want questions. I know I've been just abstract here, just plugging along, and depending on how much physics you've seen, you have some level of comfort or some level of discomfort. Travis, I know you're just taking Cal 2 this time, maybe, or Cal 3? Cal 3. So you should be fine, but any questions? Okay. I mean, it's really a crank, in terms of just computing the gradient of a function and so on and so forth. Eventually, because we're doing the same thing over and over again, it'll sink in. One of the things I would recommend, I know it's not the most fun thing to watch these things over and over again, but when you're doing something not very important, when you're Friday, you're having a beer or two talking to your friends, put my video on, just watch them. I always say, friends are not interesting people. Yeah? Physics is. So talk to them. Just say something meaningless, but so that you visit these ideas. Okay. Position vector. Making a big deal of it by making it a section doesn't really warrant that level of discussion, but suppose you're trying to locate an object, a position. You would create what's called a position vector, R. Well, what is R? Well, it is what you expected. It is x times x hat, the x coordinate, plus y coordinate, plus z coordinate. Written in the three-tuple, maybe math notation, it's just x, y, z. I mean, what else can it be? Yeah? But we're just writing in this Griffith's vector notation. Now, what I would typically like is, and you can think of this from physics too, where electric field points radially outward if you have a point charge and so on and so forth. So I would like a unit vector pointing outward. We would like to have a formula for it. What do I mean by that? It's a vector of length 1 that is radially outward. So I put R hat. Anytime I have a unit vector, just like x hat, y hat, and z hat, the hat as opposed to, what's the difference between this and this? Well, this is just a vector. This is a unit vector. So what do? I take this vector and divide by its magnitude. Right? What is this? Well, first of all, I'll denote it as R. That's what I do. When I compute a magnitude, I just remove that arrow sign. Tell me what's the magnitude of this vector? Yeah, if you're just saying that very quickly, you guys do know what's going on. So, R hat is nothing more than R divided by the magnitude of R. So it is x over, it's a long thing to write, x squared plus y squared plus z squared, x hat plus y over, because it's long, I'm also lazy, y hat plus z over, right? Where the exact square roots are repeated. One more vector, and I'm just eager to do some problems. Displacement vector. Let me appeal to your intuition. Suppose I want to know the electric field at some point, at some position R. So here is my vector R. And the question could be, what is the We haven't talked anything about E and M. We don't have so far in this class. You don't even need to know what an electric field is. You know, you do have an idea, but that's not important. We'll start from scratch. But just to ask a question so I can motivate a displacement vector, what is the electric field at, what is the electric field at R? So I might look at this confusing notation. Electric field, that's sort of my question. What creates electric field? Charge, very good. Now there could be, and that's exactly what I wanted to hear, there could be, to start off with, let's just do one charge. So, charge is located. I don't know if orange is visible on video. Is it? I know green is. A charge creates an electric field. Therefore, we say that the charge is a source for the electric field. All source points as opposed to field points. Here is where I'm interested in computing the electric field. The electric fields are created by sources. So all source points are located by R prime. The vector from the source point to the field point is called the displacement vector. There's this symbol. He uses a script R, so I'm going to put a vector on top of that. By definition, the script R is R minus so, let me write that out. R equals X, X hat, Y, Y hat, Z, Z hat. This is only notation, so do not let this confuse you. So I'm just going to call it X prime in the X hat direction, Y prime in the Y hat direction, Z prime in the Z hat direction. So the displacement vector is nothing more than and while I have 2 minutes to complete it, we will not only need the displacement vector, but also a unit vector in the displacement direction. But once again, what do? We take this vector and then divide by its, and put a hat over it. So I promise to do problems next time around. It only looks ugly. When you do problems, it won't be difficult at all. I think it's a good point to in the lecture. And I'll bring some examples. We'll do that next time around. Yeah? Any questions? Good.